Okay, let's go ahead and continue our discussion of double integrals in polar coordinates. I actually took directly from the book, Key Idea 13.3 plus 1, Evaluating Double Integrals with Polar Coordinates. Let z be a function of x and y, be continuous over a closed bounded interval r, region I should say, in the xy plane. R is bounded by these polar equations. Theta is between alpha and r is between g1 and g2 of theta. The double integral over r of f of xy dA would be the integral from alpha to beta, the integral from g1 to g2, f of r cosine theta, r sine theta, r dr d theta. Now I emphasized in the last video there that you've got to incorporate that r in there, okay? It's not just dr d theta, it's r dr d theta. Now, in the previous video, we also had the limits here being going from H1 to H2 in our open stacks presentation here. But it's the same idea here, G1 to G2, whatever you call these functions here. Okay? All right, now we wanted to see why this was true here, why we're getting the little r factor in there. So let's go ahead and discuss why that. Okay? Now, if you remember from our open stacks discussion here, we had this situation here where we had, the situation I'm going to consider here is where we just integrating over a polar rectangle. So I'm going to be taking the simplest case here to get the idea why we get that factor r in there, little r. Okay, here's our polar rectangle. Theta goes from alpha to beta. R goes from A to B here, okay? And the idea we were chatting about what? You partition up this polar rectangle into a bunch of smaller polar rectangles, okay? And then we imagine taking a sample point in each one of those polar rectangles, okay? Or polar subrectangles, if you wish. Okay, so I've got the interval from alpha to beta, so I'm going to imagine partitioning that up. Theta sub 0 is alpha, then I've got a theta 1, theta 2, all the way to theta sub n, that'll be my beta. I'll partition up the interval from A to B, okay? So R naught is A, then I've got R1, R2, all the way to Rm equals B. And then I'm going to suggest the sample point here. R sub I j tilde, theta sub I j tilde here, as you see, in the polar subrectangle R sub ij. Okay, so that means that the R value is being taken in the ith interval of theta, and the j here is indicating that the theta is being taken from the jth subinterval of the theta values. Okay, so we take a sample point in each of those subpolar rectangles. Okay. Let's go back and talk about this for a second. If you remember, when we were talking about the area of a polar rectangle, I'm going to talk about this as the lower value for the radius. Then I had a change in the radius here, okay? And then a change in the polar angle. Do you remember that we worked out that the what I was calling delta r, the area of that polar rectangle, was what? Delta theta plus 1/2 delta r squared delta theta. Okay, so we already worked that out. You can look at the other video if you need to have that redone here. But I've actually got that same page right here. Okay, if you want to still it. Okay. Now, here, when I talk about the area of the polar ijth polar subrectangle, I'll say that's delta A sub ij. Okay, so using this formula, I have r sub I times delta r sub I, delta theta sub j, plus 1/2 delta r sub I squared, delta theta sub j. I goes from 1 to m, j goes from 1 to n. Okay, and now what we're going to do is a Riemann sum. Remember, we're taking what? The sample points. Okay, taking the sample points in each subpolar rectangle. We'll evaluate the function here. Let me emphasize, the function I'm thinking of here is z equals f of xy. Okay, because that's what your book has there. That's what they were working on. Okay. Don't forget, x is what? R cosine theta, R sine theta. So we'll use that little fact there. So this becomes what? R tilde sub ij cosine theta tilde sub ij R sub ij tilde sine theta sub ij tilde times the area of the ijth polar subrectangle. Okay, so this is what we would mean by a Riemann sum for a double integral. Okay, and then I'm just going to write the double summation here. I mean the I and j here, just like that above. So I'm a little bit lazy here, but not lazy, efficient, remember? Okay, now the function evaluated at this stuff, I'm just going to call z sub ij. Okay, we don't know what it is, but it's going to be some z value here. And now let's go ahead and put our formula for delta I sub j in there. And then there I've got what? R sub I delta R sub I delta theta sub j plus the double summation, the z sub I j, 1/2 delta R sub I squared delta theta sub j. Okay, so we're just breaking this into a sum of two different terms here. Okay, got our double summations on both. And now remember, to define the actual Riemann integral, I'm going to take what? Take limits as delta approaches 0, where delta is the norm of the partition, that is what? The length of the largest subinterval. So all these subintervals, all these deltas, both the r deltas and the theta deltas, are all going to 0. Now you should recognize then what this would end up being in the limit. This would be the integral over the region. In this case, we said it was what? A whole big polar rectangle. That'd be integral from alpha to beta, a to b, r cosine theta, f of r cosine theta, r sine theta, r d theta. Yes, you notice that r getting there. That's what's happening here. Okay. On the second part, I'd be going plus the limit as delta approaches 0 of this summation. Let's go ahead and consider what would happen here. Here's what happens. I claim this goes to 0. Why is that? Okay. Guess that limit is actually 0. You guys notice what we have is actually a third order differential here in the end. See, I've got that delta r sub I squared delta theta j. Okay. If I had only had a first power on there, I would be integrating what? 1/2 the function dr d theta. But with that extra power of delta r sub I, as that goes to 0, since that other what would have been an integral, it would be a finite value, this thing actually goes to 0. There's one too high a power on that r for this to actually converge to anything other than 0 here. Okay, so this guy squishes this whole thing down to 0. In other words, what it would have been if I had only first power there, it would have been this, the double integral over r. You see what I mean? F evaluated at r cosine theta, r sine theta, dr d theta. Okay, that's if I had a first power in there. That's some finite value here. Okay, probably some non-zero finite value. But oops, I've got an extra power on this thing that's going to what? Going to 0 here. So I'm essentially multiplying this value times something going to 0. So that's going to be 0. So anyways, that's how we end up having a formula like this. R dr d theta when we are performing double integrations in polar coordinates. Okay? Alrighty. We'll do some problems here soon.